this video I want to talk about the fundamental theorem of calculus, right, which, as its name suggests, is a very important theorem in calculus. So, what this theorem says is that if f is a continuous function defined on some interval a, b, then we can define function big F of x as the integral from a to x, f of t dt. Right, so this is for x in the interval a, b. And then this function big F is continuous on AB, it's differentiable on the open interval AB, in other words everywhere except at the points A and B themselves, and its derivative is equal to small f of x. Right. So the theorem tells us that a continuous function always has an antiderivative, and this antiderivative is defined in this way. And so let's try and make sense of this theorem. And so we're doing something slightly strange here. Right? We're defining a new function as an integral. Right? But if we think of this integral in a geometric way, then maybe we can understand it a little better. Right? So the integral, right, from a to x of this function, y equals small f of t, and of course gives you that area. Right? So if we denote that area, say big A with a subscript x, right? Then we see we can think of this expression defining big F as this area. Right? So we have, we have big F of x equals ax. Right? So you can see as you vary x, right, in this interval from a to b, that the area is going to vary along with it. Right, so it's a function of x. Right, so that's a geometric interpretation of this function f as an area. Right, of course, when small f isn't always positive, in other words, when its graph isn't always above the t-axis, right, and you have to be a bit more careful with this interpretation. But this will do fine for now. So now let's see why this formula for the derivative of big F is true. Yeah. And we're going to look at the quotient big F of x minus big F of c over x minus c. Okay. Now, if you take the limit of this expression as x tends to c, then you're supposed to get the derivative of big F. Right? And we want to show that that limit is equal to small f. So we want to show that as x approaches c, this expression approaches small f of c. Okay. So let's take a point c, let's say, over there. Right. Now, big F of x, right, is the integral from a to x, so we can think of it as this area, and a big F of c, right, will be that area. Okay. So big F of x minus big F of c would be the whole yellow area minus the white area. Right, so that's the area under the curve y equals f of t from c to x. Right. So that means that we can write this as 1 over x minus c integral c to x f of t dt. Now this expression that we have here, right, that's just the average value of f. Right. Integral from c to x divided by the length of the intervals from c to x. Right. So we have the average value of f on this interval from c to x. And because f is continuous, that means that it equals its average value at some point on this interval. Right. So we have this quotient equals f px for some px in this interval from c to x. Right. So we have, say, p px over there between c and x, then sets f of px, right, and that is equal to the average value of f on this interval, right. So it turns out that this is now all we need, right, to see that the derivative of big F is equal to small f, right. Now, to finish off the argument, we need to use the definition of a limit, right, and there's no way of getting around this. Right, so if we take any epsilon bigger than 0, right, then we know that the limit of small f of t as t goes to c is small f of c, right, because small f is continuous. Right. So, because of this, and the definition of a limit, we know that we can find a number delta bigger than 0, so that if the distance between t and c is less than delta, then the distance between f of t and f of c is less than epsilon. Right. And now let's see what happens if the distance between x and c is less than delta, then the distance between px and c is less than delta. Right. Because px sits between c and x. Right. So this distance from c to px certainly is smaller than the distance from c to x. Right. Now, this means that f at px minus f at c is less than epsilon, right? You can just take t to be px in this expression, right? And now we see that this small f of px is just this quotient. So we get big F of x minus big F of c over x minus c minus small f of c is less than epsilon. Right? So for every epsilon bigger than 0, there's a delta bigger than 0, so that if the distance between x and c is less than delta, then the distance between this quotient and small f of c is less than epsilon. So we see that the derivative of big F at c, which is the limit as x goes to c, big F of x minus big F of c over x minus c, right? We see that this has to be little f of c. Right? And that's what we wanted to prove. Right? And we proved this for all points x in the interval a, b. Right? We never assigned a value to this c. Right? So this proof isn't entirely complete, right? Because we sort of assumed that c is less than x. Right? The case when c is bigger than x, right, you still get this identity. You just have to tweak it a little. Right? But the proof is given in the study guide in full. Okay. So that's the fundamental theorem of calculus. It's a very important theorem, and its proof is also interesting, right? Because we have two non-trivial applications. One of the mean value theorem, and one of the definition of a limit.